So in this lecture, let's talk about something that is very interesting, and that is the topic of topology and cohomology. Now, when you have a sequence of a billion groups associated to a topological space, that is what you call a cohomology, right? Now, cohomology can be viewed as a method of assigning algebraic invariants to a space. It is just like in homology, but in a much more richer aspect, right? Now, to start this, we will need some of the knowledge on differential forms. So I have made a lecture on differential forms, and so I would recommend you, if you have not watched it or if you don't know what differential forms are, you should go and watch that lecture first and then come back over here. So we are going to recall some of the things from differential forms, and so let's just start from there, right? So we are going to need from differential forms, recall that a P form that is written as some Fp, it is totally antisymmetric zero P tensor, right? And the exterior derivative, let me write it down, the exterior derivative it is defined as this expression over here, df of a P form, right? Mu1 to mu P plus 1, which is equal to P plus 1 factorial times partial mu 1 f mu 2 up to mu P plus 1, right? And what this exterior derivative does is that it takes a P form to a P plus 1 form, right? So if you take exterior derivative of for example 1 form, you will take it to a 2 form, right? Now also note that P forms are naturally associated to P surfaces, and that this square of this exterior derivative is 0, so that thing vanishes, right? So now we have some of these things from differential forms. Let's begin with somewhat of an unmotivated classification scheme. So let me say that for a differentiable manifold, that is M, it is differentiable and it has dimensions d. So a differentiable manifold of d dimensions, we are going to call it as some omega P of M, right? Now this thing is a space of all the P forms, right? So let me write it down over here. It is a space of all P forms. So all the P forms exist in this omega. So, well, what do I mean by when I said this thing, right? Well, we first construct a set of basis 1 forms if you can recall from differential forms, that are dx mu1, dx mu2, and up to some dx mu d, right? Now these this set of basis 1 forms, they span the entire space for us. Now with this, then any P form on this space can be written as a linear combination of independent p-dimensional collection of the basis forms. So what do I mean by that is that you can write your P form as some f mu 1, mu 2, and up to mu p, right? And that is in its upper index, yeah, times dx mu 1 wedge product. Now this this lambda type of symbol is the wedge product, and we talked about this in depth in the video on differential forms, right? So dx mu 1 wedge dx mu 2, and up to so on till you have a wedge with dx mu p, right? Now where you should remember to sum over the same indices, right? So if we consider a case where we have, for example, d is equal to 3, so 3 dimensions, and the p-ness of the form is 2, right? And we have the bases then dx, dy, and dz basis in this case. Now you can write this down using this definition as f2 is equal to fxy dx wedge product wedge product with dy, right? So we have xy, that's why we have this basis dx wedge dy, right? And plus f yz dy wedge product dz plus f zx, right? And times d z wedge dx, right? This is what you have. And so all the possible arrangements of this xy, yz, fyz, and fzx fill out the space of two forms, right? And so that space of two forms is written as this thing, right? If you recall, I said that this is the space of all P forms. So this is the space that contains all the two forms, and you can just tweak the values of these fxy, fyz, and fzx, which are the coefficients, and you can have all the possible arrangements of these fxy, fyz, and fzx in this space of two forms. Now this space of two form is on this three-dimensional space, right? Because if you remember, this d is equal to 3. That's what we chose for this example. Now notice that these linear combination provide us with a natural vector space structure, and we will understand that more in more depth later in this video. Now well, consider only the P forms on let me write this down. Consider only the P forms on this space omega p yeah, of M. M is your manifold. Now consider those P forms which satisfy this thing, that a P form belongs to this space of omega 1 of M, right, such that the derivative or the exterior derivative of this P form is 0. Now if this is your case, right, if this is something that is happening, then we call the set of all of these forms, that is a P which is equal to a P of M, we call this set as a closed set, right, if this thing is satisfied, right? Okay, now from here it should be clear that this AP of M, it has a vector space structure. So for it to have a vector space structure, what does it mean? Well, it has to satisfy some of the properties of the vector space, and one of them would be for this derivative thing, a1p plus a2p, and the exterior derivative of this should be equal to the exterior derivative acting separately on both of these, which is this thing, right? And we know that this thing has to be 0 for it to form a closed set according to this thing over here, right? Now another property for this to be a vector space structure, this thing is d of some constant k of a form, or of P form, is equal to, we could take this scalar outside and apply the exterior derivative on this P form, which should be 0, because this thing vanishes for a closed set, right? Right, now we will consider only the P forms. So next one is consider only those P forms on your this space, right, which satisfy we are considering I'm spelling satisfy wrong, satisfy, yeah, which satisfy this thing, right, that this P form. So we are choosing some other variable for defining this type of set, right? So this belongs to your space, right, and such that this B of P, this P form is equal to the exterior derivative of some other form, P minus 1 form, right? And if this condition is satisfied, right, then we say that the set of these forms, that is B, P, this set which is equal to BP of M, we call that this is exact. So it's an exact form, right, if this thing is true, right? Okay, so we will look at some examples and we'll see what do we actually mean by this, right? And at the end of this video, we are also going to see why is this useful to us as physicists, right? Okay, and these B of P, I mean this thing, the exact forms, they also have a vector space structure, right? And you can show that since the B of P 1, right, plus b2 of p is equal to dc1 of p minus 1 form, right, plus dc2 p minus 2, right, which is simply equal to d of c1 p minus 1 plus c p minus 2 c2, right, this thing. And the multiplication thing, that is this scalar multiplication, you have some constant kbp is equal to k times dc of p minus 1, which is equal to d k c p minus 1, right? And so because these two are true, that's why we say that this exact forms have a vector space structure. Well, now we have defined an exact form, and we have also defined a closed form, right? So, well, now you might be tempted to ask that if there is any overlap between these two set of forms, that is this one and this one, right? So is there any overlap between these two? Well, the answer is yes, there is, and that is because we have d squared is equal to 0, right? Any of the exact forms that are b, p must be closed, right? And that is simply because this thing that d b of p, what is that equal to, right? If you were to take this thing, but you know that this b of p, what is that? That is d c p minus 1, right? And then you add this d to it, so that is the square of your derivative. And you know from differential forms that the square of your exterior derivative vanishes, and so then this has to vanish. And because if this is vanishing, this is satisfying this condition for a closed form or a closed set, right, which is this thing over here. And so therefore then I can say that any of the exact forms must be closed, right? Okay, so now what is really useful though are the forms on the set of this one, right, which are not in the set b of p, right? So yeah, we are going to be looking at the forms that are on this set here, but they're not in this exact set. That is the set of closed but not exact forms, right? So closed but not exact, right? And these end up giving us very useful topological information about a space, right? And that's why we are going to focus on purely this one, right? Now, to go even a more deeper, we will introduce the quotient, which is a vector space. And so let me write this thing over here, quotient. I hope I spelled that right. Right, it's a vector space, and we will see what is this thing really called, right? We will see very soon, right? Or actually, just let me go ahead and say this thing, that this thing h of p right? This thing, what we are going to just define right now in a bit, it is known as the P-th Cohomology of your manifold M, right? And we are going to start with calling this as the as a quotient, right? A vector space. So let's define this. What is this going to look like? Well, this H P of M is equal to the ratio of your closed form to the exact form. So that is A P of M divided by B P of M, right? That is two vectors in this A are considered to be the same if they differ by an element of this B, which is the exact form, right? So let me just give you an example, right? Say you have this thing A P 1 minus A 2 P, right? So you have two closed P forms, and the difference of that is equal to an exact form, right? Then we say that A1 of P is equivalent or equal to A2 of P, right? Now, well, for an intuitive idea of vector space quotients, we will consider, let's consider in 3 dimensions R3, which is X, Y, and Z. And let's consider that this thing is quotiented by R2, which would only have X and Y. Well, then if we have two vectors, say v1 is vxi hat plus vyj hat plus vz k hat, let me just correct this, yeah, vz k hat, right? And you have some other vector, we'll call it v2, which is this vector v1, right? And added to it are these two components of this x and y. So you have some u x I hat plus u y j hat, right? Well, if you have this thing, right, this thing, so your R3 is quotiented by R2, then these two vectors in a quotient space are considered same, right? That is what I meant by this thing, right? So I hope you're getting the idea. So, well, what this is saying essentially is that I can simply ignore the x and y component, right? If I do this quotient, I can ignore the x and y component, and what I am actually truly specifying is the z component, right? And so effectively what happens is that this division, which is xyz, r3xyz over r2xy, this thing gives you r1, right? So you're going in 1 dimensions, and z component. This is of course a very weird abstract division that is happening over here, right? But yeah, this is what do we get, right? So if we take this quotient, now unfortunately the dimension of vector spaces that are your A P of M and B P of M, right? The dimensions of these, I'm sorry, I forgot to include this quotient. We will have this thing as well, right? So the dimensions of these are not so obvious, right? And let's see, because however, the dimensions of this thing, right, which are also called the dimensions of, let me write this down over here, the dimensions of HP, which is the cohomology, the P-th cohomology of your M. They're called the they are called the P-th Betti numbers, right? Betti number of what? Of your manifold M, right? And this P-th Betti number, right, the dimensions of your P-th cohomology is a useful characteristic of your M. Right, now with all of this, let's do some examples, and in the course of doing these examples, we will do some honest to God calculations, right? And again, yeah, let's start with considering the zeroth cohomology of M. So what do I mean by that is, well, let me write over here examples. Yeah, so the first one we are going to start with is the zeroth cohomology of M. So that is simply written as H0 of M, right? And well, in this case, if we have P is 0, right? That's what we have, P is 0. Then we are just talking about smooth functions. What that means is we have F, the functions, they belong to C infinity of M, right? Where this C infinity, simply it means that you can take as many derivatives as you would like and it won't be a discontinuous function, right? Okay, so this thing is on M, right? And now the elements of your A0, which is the closed forms, right, are closed, right? Again, so the elements of this are closed. I spelled that very wrong. Closed, right? Okay. Right, so what that means is that we would have this exterior derivative of the zeroth form is equal to 0. Or you could also say that the exterior derivative of your function in this would be df over dx mu, right, which would be 0. So locally these functions are locally constant. However, if M is composed of a disconnected pieces, right? So let me actually draw that here for you. So if we have space M, right, let's consider this dotted line our space M, and in this space you have some disconnected pieces of M. So we'll call, let me instead use a completely filled line. What I mean is something like this. This is your M1 and this is your M2. Now these two pieces, they are disconnected from each other, right? Then a locally constant need not to have the same value on each of these disconnected pieces, right? It does not have to be the same. What do I mean by this is, for example, it may be that you have your f of x1 mu, right, is 0, and that is for this thing, right? And if you compute your f of x2 mu, which is on this one, that could be, for example, 1, right? So it does not have to be the same on these two disconnected pieces. Now clearly this thing A, the zeroth form, of M, right? This thing forms n dimensional vector space, right? So it forms n dimensional vector space. Over here, what is n? N is simply the number of these disconnected components, right, of M, where the constant value of f on each piece, it serves as the vector components. So these values, right, they serve as the vector components. So so that is, what do I mean is this thing A0 M, right? But we have talked so far about this thing, right, which were the closed forms. We could then but we know that we talked about the exact forms as well. So what about this thing, right? What about the exact forms? Well, it really turns out that this thing B0 of M, right? If we are talking about the zeroth cohomology, what happens is that this thing, we have this thing, right? Now this thing would require for us that B0 should be equal to DC minus 1, right? I mean, this is in the superscript C minus 1. But we know that this thing is not possible, right? So it's impossible. And what then that implies is that B of 0 is empty, or it's an empty set, right? Because this thing cannot happen. So then therefore what we would have is that this zeroth cohomology of M is then simply this thing A0 of M divided by B0M, which would simply be equal to only A0 of M, because B0 is empty, and this would be our K, right? This thing. And then over here, K is your it's the Betti number, right? So the zeroth Betti number, K, right? It's K. It simply counts the number of disconnected components of M. So let me actually just write it. So this thing counts the number of disconnected components of your space M, right? And over here, the zeroth Betti number, the zeroth is for the P, right? So we are talking about the zeroth cohomology. That's why we have over here we said zeroth Betti number. Right, now to we could even go for a higher P, right? So to evaluate this thing with P, instead of being 0, if it could be a higher number, what we need to do is we will need to consider specific spaces, right, that are M. So let's talk about now the this thing, right, H1 of this real field, right? So the real space of real numbers. So this thing does not look neat. Yeah, right. So let's talk about this thing now. So this is the first cohomology of your space of real numbers. So a one form in this can be written as a one form is generally written as this thing, right? So it's f of x dx, right? And now because is a top form, right? What that means is, if you have watched my video on differential forms, that simply means that your P is equal to the dimensions, right? So what that implies is then you call your form a top form. Right. Now we must have, if we have this thing, if we have a top form, that further implies that you should have df of 1, the exterior derivative, should vanish. Now, hence all 1 forms in this case are then closed, right? Because this thing also implies that the forms should be closed, right? So then all of these 1 forms, they will be closed. What that means is this thing A1 of this space of real numbers is equal to this thing, right? Okay, so again, what about then the exact forms, right? What I mean is that when can this thing equal to dc0, right? When can this thing be true, right, on your space of real numbers? Well, what I'm asking is, more explicitly, I can write that down as b1 is equal to b of x dx, which is equal to dc0, right? Because it would be dc p minus 1, but p is 1, so 1 minus 1 is 0, so dc0. But then this thing is equal to this thing dc of x over dx times dx. Now the question, what I'm saying is that if given any smooth b of x, right, can we find a c of x, right, such that the b of x is equal to this thing over here, right? So let me actually write this down, what I'm saying. So given any smooth b of x, can we find a c of x such that the b of x is equal to dc of x over dx, right? Can we find this, right? Well, if you know from your calculus, we have a fundamental theorem of calculus, and that guarantees that c of x is equal to the integral of b of x dx, right? And that does the trick for us. And so the answer is yes, we can find c of x such that that condition is true, right? This one. So, and that's because of the fundamental theorem of calculus, right? And that guarantees us this thing. So we have then found out that A1 on your real space is equal to omega 1 of your real space, which is equal to your B1 on your real space. And so in this case, what happens is then hence H1 on your real space, this quotient, which is equal to A1 real space over B1, right? This thing vanishes. And then the first, you could say the first Betti number, what is that? Of R, it is 0, right? Now, in fact, what we can do is this can be generalized to arbitrary Rn, right? Some arbitrary Rn, leading us to the Poincare lemma, right? So Poincare lemma. Again, what I'm saying is we can generalize this whole thing that we have been doing to some arbitrary space of Rn, right? Which will lead us to this Poincare lemma, and that is that your H P of Rn, right? And the cohomology, the P-th cohomology of your Rn space is equal to your space R, right? That is when you have P is equal to 0, and it is equal to 0 when P is not equal to 0. And that's what we have been seeing from this example that we were doing, right? The one that we did for this P equals 1, and here we did for P equals 0, right? So you see then for P is equal to 0, you have some Rn, right? Or in this case, I wrote Rk, right? But when your P is not equal to 0, which was this case, your Betti number is 0, right? This thing. So that is what we have from this Poincare's lemma. Now, this one is just a statement that Rn has one connected component, right? On the other hand, this thing, right, this one, or let me just, this one, this says that all closed P forms on Rn are also exact. What I mean by it is that this AP, which is a closed form on Rn, is equal to the BP on Rn, right? So then what this means is that all these closed forms are also exact, right? Well, you may ask me what is the importance of this result, and it is simply that it tells us that the difference between a closed and exact forms is a global property of the manifold. So it depends on the manifold, right, globally. Now you might ask me why or how can I say that? Well, that is simply because locally any manifold, it looks like Rn, right? If you look at a manifold locally, it will look like Rn, and so locally any closed form is then exact, right, because of this thing. So the problem arises when we extend this thing to the entire space, right? That is when we are not looking at it locally. But that is what this topology is all about, right? So topology does not care about the local structure. Topology only cares about the global structure, right? So let's consider another example. Let's talk about the one cohomology of S1, right? In topology, S1 is simply a circle, right? S is a unit sphere, and we write it as some Sn, where if n is 1, we refer that to as a circle, right? And if n is 2, it is a sphere, right? Your ordinary sphere. Okay, so let's talk about the cohomology of a circle, right? And this time it is more natural to use a basis form of a d theta, right, instead of using dx. So in this case, then you can write your one form as f as a function of theta times d theta. Remember, when we were using dx form, then we had our one form as f of x times dx, and now simply we are using changed the bases, right, to theta, and then the one form will be written as such. And again, we find that since over here p is equal to d, right, the dimensions, this thing df, then df of 1 would vanish, right, because this thing implies it's a top form, and that simply implies that the exterior derivative of the form is 0. So then again with this, then once again what happens is a 1 of s1, right, is equal to this space 1 of s1. That means that all the one forms on s1 are closed, right? So then what about the exact, right? What about the exact forms? From our previous argument, what we want to do is we want to find b of theta, d theta is equal to dc of theta over d theta times d theta, right, which we could try to get from this thing, that c of theta, this thing comes from the fundamental theorem of calculus, is the integral of b of theta times d theta. Now the new ingredient over here is that all of the functions that are involved must be periodic in theta, right? And well, this for functions to be periodic in theta is what it means to live on s1, right? So they have to be periodic in theta if to have this circle, right? So well, what we could do over here is we could expand b of theta in a Fourier series, because in Fourier series we have this sine and cosines which are periodic functions, and well, we will see what happens, right? So what we will do over here is we will expand our b of theta in Fourier series. So if we do that, then we have b of theta is equal to 1 by 2 a naught. I'm simply expanding b of theta in Fourier series. Sum n is equal to 1 an cosine of n times theta plus bn sine of n times theta. Again, this let me just mention this thing, that when I use this theta under this gamma symbol, I mean cosine of theta, and when I use theta under this sigma symbol, I mean sine of theta. So it's just it just helps me to, well, it's a because I'm lazy, right? I cannot write cosine theta and sine theta on and on again. So yeah, then we have expanded b of theta in a Fourier series, which is this thing over here. Well, what we discover from this is that c of theta, right, is periodic only if, well, if you look at this thing, we only have periodic functions in this part, right? So if a naught is 0, then we can say that c of theta is periodic, right? And that is again simply because for any n that is not equal to 0, we are just integrating sine or cosine, which gives back the periodic functions, right? So when you integrate sine or the cosine or sine, you end up with periodic functions, right? So the set of exact one forms, which are a set of exact one forms, which is this, is almost the same as, we can say it is almost the same as A1 of S1, right? The closed forms. The difference only being that is parameterized by a single number, and that was A0, right? And now hence we would have H1, the one cohomology of S1 is equal to A1 of S1 over A1 of over B1 of S1, right? And that would be simply equal to R, right? And with this, then the first Betti number, let me write it down over here, the first Betti number of this S1 is +1, right? Now from here it would be nice to work with more examples, right? But then it would be tedious as well. So instead what I will do is I'll talk about a few interesting and useful results, and then try to give all of this an interpretation, right? So then this then leads us to talk about the Poincare's duality theorem. Right, so we are done with talking about examples. We are moving to some of the interesting results, right? So one of the result of all of this is the Poincare's duality theorem, which states that I'll just write it down, right? On a closed manifold of d dimensions, what that looks like mathematically is MD, right? We would have BP MD, and I'll just tell you what BP is. Of MD is equal to BP minus 1 MD, right? And this BP of MD, that is the Betti number for MD. So it is Betti number for MD. Sorry, D would be an upper index. Yeah. Now with this then, well, I'm not going to do the calculations for this example that I'll just tell you. I'll just tell you what it looks like, and in fact it would be a good exercise for you to do the calculations, right? So with this then I will just list down the cohomology of S2. And in this you could use you will use this you will get or let me just do this, right? Let me just write these cohomologies down, and then I'll tell you what I'm saying. So we would have this zeroth cohomology of S2 is equal to R1, and that is since this thing only has one connected component, right? And you could or you should do this by yourself using all the using the knowledge that you gained from the above examples that I did for S1. Now you could have the first cohomology of S2, right, is equal to 0, and this you can prove independently. And finally, let's talk about the the second cohomology of S2, right? And that is your R1, right? Now, this can be simply proved using the Poincare's duality theorem, which is this thing, right? Okay. Now, let me just end this video with giving giving all of this that we have been talking about an interpretation, right? And so to fill in some of the unproven results that I might have used in this lecture, and to hint at why all of this is useful to us as physicists. Well, for that you should recall from differential forms that a P form, that is a P, it is naturally associated with a P dimensional surface. Right? It's naturally associated to a p-dimensional surface that is represented as this thing, and that is because since this integral is well defined, right? And I talked about this in depth in the video on differential forms, and even in the topological field theories, right? So if you have watched that video as well, it would be even more useful to you, right? But differential forms is something that you should really know about. So from this then I can say that and another way to think about cohomology is to think about topologically distinct p-dimensional surfaces in the space M. And in fact, this is the basic idea of homology, from which cohomology can be obtained by dualization argument. And it turns out that we only have to focus on the closed surfaces. So you could consider with this, H0 M, right? So the zeroth cohomology over M, and that is how many types of, this tells you how many types of zero dimensional surfaces or points, right, that cannot be deformed into each other, right? So I'll show you what I mean, right? Into each other. Now this clearly, this it counts the number of connected pieces of M. And that is since, let me draw this thing, since we have this M1, right? And you have some 2 points in this. Now you can use these 2 points in M1 and deform them into each other in this space M1. But if you were to have another space M2 and you have 2 points in M2, well, there is again in M2 you could deform these 2 points in M2 itself into each other. But if I were to take 1 point from here, right, and 1 point from here, then I cannot deform them into each other because they exist in completely 2 different pieces of your whole manifold M, right? So there could be a whole manifold M, right, like this, and these M1 and M2 are just the connected pieces of your M manifold. Right, now with all of this, let's ask why why is all of this useful, right? So it really allows us to determine whether two spaces are topologically the same. And in these examples that we talked about, right, in all of these examples that we have talked about, it is pretty obvious, right, that thing that that you could determine whether the two spaces are the same topologically. But remember that many spaces are defined abstractly. For example, we could have an embedded surface which is defined by a constraint equation. Now, well, this was a bit mathematical. We could ask that why is this useful to us as physicists, right? So what about the use of this, or all of this thing that I have talked about in physics? Well, one of the use that I could think of, and it might be even interesting to you, is that in string theory, we have extra dimensions, right? I'm pretty sure all of you know about this. So these extra dimensions, they are typically considered to form small compact manifolds, right? So very small compact manifolds. That's why we say that these dimensions are really small. And we also have something that we call this D-branes, right? D-branes. And so then it becomes useful for us to know how do these D-branes can wrap the manifolds and still be stable, right? And well, that is just diving into string theory, and this knowledge of topology and cohomology is extremely useful if your main focus is on string theory, right? And of course, it has many other uses as well. For example, in topological field theories, we talked about this how we could make a theory purely topological, and we considered the example of electromagnetism there, right? And we made electromagnetism, the action for that, we made it purely topological. So there are many uses of cohomology as well in physics, and one of which I was just telling you about is in string theory, and hopefully that was one of the most interesting one. So with this then, that's the end of the lecture.